defining a few dimensionless numbers. We were defining again the Dahm-Köhler numbers for heat and mass conversion, and we were defining a biomodulus for heat and mass. And these will occur also in the following. But first, I will just say a few words about the volatilization, and which takes place when the particle or part of the particle has reached a certain temperature. And then the molecular structure is turned into molecules depending on its own properties, its own characteristic temperature. And of course, drying has the same properties. Drying takes place when the temperature has reached the evaporation temperature. And this could take place in the particle simultaneously if it is a small particle, small BO number, or gradually if it is a large particle with large BO number. But there is another complication that I would like to illustrate here. We have two cases. We have the cold case and the wood case. In the cold case, when the particle is heated, the volatiles and the moisture is released rather much in the same way around the particle. It is called, because of the structure of the particle, is isotropic. It is not very much changeable in different directions. But there is a flow out, and this was the flow that I called previously the Stefan flow, that could impede the transfer of heat and mass from outside to the surface of the particle. But the effect is not so big, so probably it can be neglected in many cases. However, it exists, but rather small in most cases. In the biomass particle, particularly in wood, the fibers are directed in a particular way, and the gases leave through the fibers. So they tend to leave in a particular direction, whereas the heat and mass transfer may take place in a perpendicular direction. So it is much more complicated than the coal in that respect. In general, you could say that fuel plus heat is equal to volatiles plus char. Volatiles is the gaseous product that is leaving when the fuel is heated, and char is what remains. The energy of the reaction, or the heat of reaction, is rather not so big, so we could say that it is negligible in most cases. Neutral, it says here. But you can develop this even further. You could say that the volatiles consist of gases, which are non-condensable gases, and tar, which are gases that could condense at a certain temperature, usually in the surrounding, not in the furnace or reactor itself, because there the temperature is high enough. So this is only important in gasification, for instance, and I don't think it is important in boilers. It's just gases. They react in different ways, but they will react more or less before they exit. Well, there are different ways of looking at this. You can make a model of a single reaction pyrolysis like this, that the volumetric, in this case, reaction rate is equal to the density change with time. And density is, of course, the mass divided by volume. So this belongs to the reaction rates that I have defined yesterday, So it is a reaction rate here, but expressed in terms of density. And there is a change of density that can be expressed as the current density minus the final density, the density when all the volatiles have left. That is the char, probably, char density. So here is the current density of the particle, and this is the final density when the volatilization is finished. Here is just a reaction rate coefficient, just like I have mentioned before. And this reaction rate coefficient can be expressed in terms of an Arrhenius equation, just like in the cold combustion. We have pre-exponential factor and we have some kind of activation energy to be determined empirically by experiments at a certain temperature. And this is the, as I said yesterday, it's the gas constant, which is included there for traditional reasons. Okay, so we can integrate this equation, and we integrate it from the initial case to the final case. And then we will get an equation that looks like this. Of course, it's just an integration of this one. And I do so because I wanted to define a time constant, which when the exponential is 1, it is when the argument of the exponential is 1, like this. This time is called the time constant. So the time constant for pyrolysis is this quantity, and this is the reaction rate coefficient of pyrolysis. Okay, let's continue. Again, this equation that we always like to use, but in a very simplified way. This is the transport equation. The transient term for the temperature here, and the dimensionless temperature, and this is the diffusional part. I have not included the convective part. So this can be solved. And in fact, I don't know how to solve it, but I can look up in a textbook which gives the solution of simple differential equations, partial differential equations. And I can get that depending on the boundary conditions. For BO large, I get a solution like this, that the temperature is a function of BO and an exponential term, which is function of the Fourier number. If BO is small, I get this solution. Simpler, it is just the BO times the Fourier number here. I don't know exactly how to treat this, but I do it in a very simplified way because I just want to get some idea, not the exact solution. So I say that this term is unity, and I neglect this, it's maybe unity more or less also. So I'm only interested in the Fourier number and the BO times Fourier number, which I have put equal to 1 because it is the time constants that I'm looking for. And I just want to have the feature of the time constants, which I get here. I get the time for large particles is proportional to the diameter squared, whereas for fine particles, it's proportional to the diameter. So you have this distinction between the large particles and the fine particles, as long as you have heating control, thermal control, transport control of the evaporation and the volatilization. We will come to the next picture. Next figure will show the results. This is the volatilization time expressed in time in the time constant, and then I have the fuel particle size here in millimeters, but in a logarithmic scale. So we have 1 here, 10, and so on. Then yeah, the diagram looks rather complicated, but if you focus on the red lines, this red line is for the large particle. It's proportional to diameter squared. You can see the inclination of the curve. But for smaller particles, it is proportional to the diameter itself, linearly proportional. And then for very small particles, there is no proportionality, but here I have calculated the time constant for the kinetic reaction. And it is around here. So for very small particles, much less than 1 millimeter, we have kinetics control. For little larger particles, around 1 millimeter here, we have convection control, I can say. And this is then the diffusion control. And I have compared this with some data from a book here, which present a number of a collection of empirical data from the literature, because this time of the volatilization has been determined quite frequently and published. For instance, one result is like this, that the time of the volatilization is proportional to the diameter of the particle to the 1/6, and maybe there is a function of temperature also, but basically it is proportional to this 1/6, and that is rather well. It agrees rather well with this curve, whereas it does not agree with this. But it's no wonder, because the red is just a very rough approximation, so it intends only to give an idea. But whereas this black is a measurement, so it is more precise. But it's not so precise, because there are many factors except the diameter that may influence, particularly in this low range where BO is small. BO small means that the external heat transfer may affect, and there are many parameters that affects the external heat transfer. So I think this is why there is such a large range of experimental results in this area, while in this area there are it's not so scattered, and this is because here with large BO number, it is dependent more on the internal thermal conduction of the large particle. So this is, and thermal conduction is not so much different from one particle to another, whereas this is influenced by the external boundary conditions, and there is such a lot of influence. It's another interesting thing that the diameter, the diameter of irregular particles can be calculated by using surface to volume average diameter. You can see in the lower picture here a number of disks and rods, and finally a spherical particle. And all these together have been converted into surface to volume, several surface to volume average diameters. And they have been plotted, and these are the diameters that form the basis for this relationship. So it works quite well, despite what I said before about the porous structure and the anisotropy of wood. This is wood particles. So even if that has an influence, it's not dominant. And this can be represented rather well. Okay. Just to give verification on the previous results on the order of magnitude, at least, I have looked at some other presentations regarding pyrolysis as a function of particle size. Particle size in the logarithmic scale on this axis now, and the temperature on this axis. So for the typical temperature range of our interest, For particles more than 1 millimeter, we are definitely in the thermal range. And for particles much less than 1 millimeter, we are in the chemical range, where we have the kinetic regime. And then there's, in this investigation, there is a large transition regime between these two thermal and kinetic regimes. So this is, and in fact, the BO number are given. It is for large BO numbers, and this is for small BO numbers. So it is possible to say some general things about the volatilizations. Okay, I made an experiment before. I showed an experiment, this one. This was a wood case, and wood was modeled by 3 components: hemicellulose, cellulose, and lignin, and they were investigated in a thermal balance to get the rates as a function of temperature for these 3 components. You can see the hemicellulose is released at a lower temperature than the cellulose, and lignin is probably at the highest temperature. It's more stable, but this hemicellulose is released at a temperature of about 300, or a little more than 300 degrees centigrade. You can say, if you transfer this to centigrade. I will compare later with this curve. And I would like to mention that in wood, we have only 3 components. Wood is composed by these molecules, very complex molecules, but only 3 types. Whereas coal is composed by a large number of molecules, more or less complex. So coal cannot be represented in such a simple way, but instead one uses a statistical treatment of the various molecules of coal to get some statistical curve of the rate of the volatilization as a function of temperature. Okay, so I come back to these 3 rates. Now we have the time here, and we have the temperature here in degrees centigrade now. So 300 is perhaps somewhere here. And below 300, nothing happens, but here it starts to happen. And you have the 3 curves, hemicellulose, cellulose, and lignin at larger temperatures. And then this is compared with the thermal times calculated for large BO number particles, which are up to 10 millimeters, 6 to 10 millimeters. They are large BO numbers, and so they are controlled by the thermal conductivity, and the thermal conductivity is not very much dependent on temperature, so they are rather constant, independent of the external temperature. Okay, so what we can read from this diagram is that at low temperatures, the volatilization is controlled by the kinetics. These are the most important rates at low temperature. Whereas at the high temperatures that we are interested in combustion, the kinetics are very low, and they are not so important. Instead, the thermal transport is the important one. So this confirms again that thermal transport is probably most important in fluidized bed combustion, because we have rather large particles. Here is another example of the volatilization of different sized particles, which I think is quite interesting in its simplicity. We have small particles and we have large particles. This is the particle size. We have these extremes. And we have the conversion rate here and the time here. For the small particles, yeah, I have to say the solid line is the evaporation of moisture, and the dashed line is the volatilization. So if for the small particle, the particle first releases its moisture, and then after some time its volatiles. So they are sequential here. But for large particles, they are simultaneous. So there is a difference between small particle and large particle in this respect. And this can be explained by the BO numbers that I showed you previously. For the small particle with small BO numbers, the particle, if you present it like this, like various temperatures in this direction, and the size of the particle in this direction, so the whole particle obtains one temperature, and with time, temperature increases simultaneously in the entire particle. So when the particle temperature has reached 100 degrees, more or less, we have the drying, and then when it reaches the volatilization temperature, the volatiles are released. So this is why they are sequential. Whereas for the larger particles, there is a wave of temperature moving inside the particle. We have quite a different temperature profile with large gradients of temperature inside the particle. And the difference between the volatilization temperature, which is here, and the drying temperature is very small. That is why they almost, or they more or less coincide. This is an interesting phenomenon related to the BO number of the particle, or the size of the particle, you could say. Yeah, I can just summarize saying that we have been discussing two sets of dimensionless numbers, each of them valid for heat transport or mass transport, or heat the release of pyrolysis because of heating and the transportation of mass. So for large BO numbers, the internal heat transport controls. For small BO numbers, the external heat transfer controls. So that is for the BO numbers. And then the Damköhler number is, you can express that as a ratio of conduction or convection and reaction, time of reaction. So when this time is large, when the transport time is large, then the transport condition control, Damköhler large. When the Damköhler is small, this one is large and this is smaller. So then the pyrolysis rate controls. And this is very classical in the volatilization field. And particularly, yeah, it is very much liked by many researchers, and particularly in biomass, because there was very much research in biomass related to pyrolysis, because the volatile content in biomass is so important. And then they invented a Damköhler number, which is inverted pyrolysis number. So they invented the wheel, so to say. The researchers that introduced this pyrolysis number were not aware of the Damköhler number or about the Thiel modulus. So they invented a number of their own. And many of the people who deal with biomass refer to this pyrolysis number because they are focusing on biomass only, and they are not aware of the rest of the field of knowledge in the combustion theory. Personally, I prefer using the Damköhler numbers. They are equal. I think they are equivalent, but I prefer using the Damköhler number because Damköhler was the first, and also because it is more general than the others. It can be applied outside the particle, inside the particle, and it would be the same as the Thiel modulus, and it is the same as the pyrolysis number. Okay, so I have some more to say about pyrolysis, but I am lack of time, so I would like to go directly into char conversion, the remaining after the volatilization. In biomass, it is maybe 20% of the particle of the energy in the particle that remains. In coal, it depends on the rank of the coal. Anthracite has very little volatiles, and the lignite has maybe 50 and little more % of volatiles. So coal is more variable. Biomass and related waste products have more volatiles. But here we have the char. And important question is whether it is controlled by kinetics or internal or external transport. And also how to describe the reaction rate, whether to use a power law or a multi-step reactions. This is what I'm going to discuss a little. Yeah, when we start to oxidize char, which is mostly carbon, then the carbon reacts with oxygen to form carbon monoxide or carbon dioxide. Both reactions may occur simultaneously at the same amount of oxygen. So this is a problem that we don't know exactly what happens on the car surface, whether we get carbon dioxide or carbon monoxide. What we know is that under combustion conditions, sooner or later, the carbon monoxide will be oxidized to carbon dioxide, but this is outside of the particle. So we are now at the surface of the particle or inside of the particle. And those are both exothermic reactions. Okay, so it can be expressed in many ways, but sometimes a simple combined reaction is used. In this case, with F as the molar ratio of carbon to oxygen. And if in this equation, this is a parameter. So if F is 1, then we can see that we get 0 CO2, and all of the carbon is converted to CO2. If F is 2, then we get only CO and we get no CO2. So you can see this is a kind of parameter that you can use to express the reaction from one extreme to the other. And this F has been investigated in many investigations, and I just show the sad result here that there is no agreement between different investigations. So it is so difficult to measure. So there are so many, for that reason, many different results. One difficulty that happens is you don't know for certain if the reaction takes place just outside of the surface of the particle, and then it affects the particle, or if it takes place far away from the particle where it does not affect the particle. So this is one difficulty that has caused these problems. There are some very careful investigations. I just mentioned one of them here from Toniotti. He measures the ratio of carbon monoxide to carbon dioxide with such a formula like this. He includes also the partial pressure of oxygen at the surface, but we can forget about this. Let's not discuss this here, but only this term. It shows that if the temperature is high, then CO2 will CO will dominate. If the temperature is low, CO2 will dominate. So in our high and low in this case means pulverized cold combustion and fluidized bed combustion. So in pulverized cold combustion, CO will dominate as a primary product. But at fluidized bed, we have lower temperatures, such as 900 degrees centigrade, perhaps, the char temperature. And then we have more CO2, or more or less the same CO as CO2. And often it could be more CO2. So it doesn't make it easier, but we have some idea at least that it depends on the temperature. That is the only thing I can say for certain. Otherwise, this is very vague. It's very difficult. It's important though, because the energy of the reactions are different. The heat of reactions are different in this reaction and in the CO2 reaction. So if the oxidation goes to CO2, much more heat is released than if it only goes to CO. This means that the char particle will attain a much higher temperature if all reactions go to CO2 than if it goes to CO. That is important. We have more reactions that could take place, and that is the gasification reaction between carbon and CO2. CO2 that is produced and CO2 that may exist in all combustion environments, also not only in gasification environments, but the concentration is usually low and the temperature is low. So this is not very fast reaction, and it doesn't take place very much at a temperature of 900 degrees and also at rather low CO2 concentrations. So otherwise, it would consume some of the heat. It's an endothermic reaction. Yeah. This reaction is not equimolar. So 1 mole of C requires half a mole of oxygen and releases 1 mole of CO. So half a mole of oxygen diffuses towards the particle, while 1 mole of CO is released from the particle. So there's a non-equimolar situation, which produces a Stefan flow situation. But since the CO is not so, since this reaction is not so dominant in fluidized bed combustion, the Stefan flow may not be so important also. But it exists, and one should think about it as a possibility. There are some other reactions that I would like to mention at the same time. Even in a combustor, you may have water vapor, of course, and that may gasify the char. Water vapor has a faster rate of gasification than CO2, but still the concentration is rather low under combustion conditions, and the temperature is not extremely high. But in any case, you can say that the temperature has to have a certain level in order for the thermodynamics to go to the for the thermodynamics to. Do you hear me? Can you hear me? Sachin, can you hear me?
Yes.
So
yes.
It's okay.
Yes, sir.
So I wanted to say that yes. This is the thermodynamics. This is not the rate of reactions. This is the end situation. If the rate is very fast, you can come to such a situation where everything is reacted, but then the temperature has to be sufficient. Also in the CO gasification reaction, temperature has to be sufficient for thermodynamic reasons, but the rate is slow, so it will not reach very far. Here you have another gasification reactions with hydrogen, but this takes place only at very low temperatures. So this is not of any interest at all during combustion. The rates I mentioned that they are fast or slow, we have them here. This is the rate in a logarithmic scale, and this is temperature, an inverse of temperature actually. So the highest temperature is on this side, the lowest on this side. And I have drawn two curves only, one for combustion, one for gasification. Actually, it's a very large number. It's a mess of different results in both cases. It's very difficult to determine exact value, but I just take this some kind of average value here. What I wanted to say is that at a certain temperature, we may be somewhere here, we have two orders of magnitude of different in the rates of combustion and gasification. So under combustion situation, where we have oxygen present, the oxidation reaction takes place first, and the other reaction will take place only under certain circumstances. So in a combustor, gasification is not important. And even in a gasifier, if you have some oxygen, it will oxidize first, and then the gasification reactions come afterwards. This is the regimes of char combustion. This is very important, very fundamental for the understanding of the conversion of a char particle. Again, it's always spherical particles, and there are three cases. Case 1, case 2 is not included here, but there are two, case 3. I come back to case 2 later. Case 1 means that it's a homogeneous case where the rate of reaction is very slow, and transport is sufficiently fast to be for high reactant to be present in the entire particle. So the particle is converted gradually, the entire particle at the same time. In combustion, this would not take place because the rate of the reaction is too fast, but it could take place at low temperature gasification. And this is case 1. The case 3 is more common in combustion. This is where we have a high rate of reaction, and we have several cases here. We have one case where we have a certain concentration of a reactant, and then at the surface it is consumed completely because of the very fast rate of reaction and fast diffusion in this boundary layer. So everything is consumed here. But we have a special case where it is consumed only gradually, and where it's a resistant. It is consumed at the surface, but it is reduced only gradually because there is a resistance in the boundary layer here. So the reaction takes place on the external surface of the particle because it's so fast that as soon as it reaches the particle, it reacts. And then, we have this case where the particle, it starts here, obviously. This is the original particle, starts here, then it reacts on the surface more and more until it disappears. So this is called the shrinking sphere case. Shrinking sphere case, case number 3. And this is similar to the shrinking sphere, only that it is only that something happens here on the surface. There is an ash layer remaining at the surface because the coal may consist ashes involved in the coal matrix. So when it reacts, the ash is left behind, and the more it reacts, the thicker is this ash layer. So it is similar to this, but there is an additional resistance here, namely the transfer of gases in the ash layer. So here there is no resistance in the either in the external boundary layer or in the ash layer. Everything reacts on the surface. Here it is resistance in the boundary layer and resistance in the ash layer. This is the more common case. So this is called a shrinking core. And this is also case 3. So these are very, very important. I illustrate them again. Suppose we have a particle of the size, this is the surface of the particle, this gas concentration, and then in case 1, we have a diffusion. The diffusion everywhere, reaction rate is slow, and there is no problem. It will maintain its concentration while the particle is reacted. But in the case 3, as I said, there may be some fall in the boundary layer because of diffusion resistance, but here at the surface it is reacted, so the concentration is always 0. Case 2 is an intermediate case. There are 2 variants. If we suppose that there is no resistance in the boundary layer, case 2 comes to the surface of the particle, but it is slow enough to penetrate inside the particle, so there is a concentration gradient inside the particle, like this. It could be slower or faster. It depends on the concentration gradient or on the diffusion rate inside the particle. Here we have some diffusion outside the particle as well as inside the particle. So this is another variant of case 2. So we have these 3 cases with their different variants, and these are the cases that we will treat always in combustion of large particles. Case 1 is not important in combustion. Case 3 is the most important one, but case 2 can happen. Okay, so we have to determine. Yeah, this is an experiment that I would like to illustrate this, what could happen. Yeah, we have a reactor here. You can see the reactor here, and then we have a char particle, which it is a char particle that is kept here at a certain position. And in this case, there is a thermocouple inserted also in the char particle to measure the temperature. We have a similar thing here. But here it is, kept in some way. The thermocouple is probably here inside. In this case, it's an empty reactor. And we can also use an optical pyrometer focusing on the surface of the particle to measure the surface temperature of the particle. In this case, it was inserted in the fluidized bed, so we cannot use an optical pyrometer, but we can measure the internal temperature of the particle. So we want to operate, and we make a model of this. This is the rate of the reaction, rate of consumption of the mass, and then when mass is consumed, heat is produced because of the heat of reaction, and this is equal to the heat transfer to the surface by expressed by a heat transfer coefficient, the surface of the particle, and the difference in temperature between the bed and the particle. The surface of the particle. So we will see what happens in different cases. I start like this. This case, we have 800 degrees always in the reactor. We have in this case, this empty reactor, we have 21% oxygen. Yeah, and we have 21% oxygen also in the fluidized bed reactor. And then we measure what happens during time, and we measure particularly the temperature as an indication on the reactions. So what has happened here is that the thermocouple measuring in the center, which is the crosses, no, it's this line. This is internal particle center, this line. And then with the optical barometer, we measure on the surface. But there we measure this curve, very high temperature, for 1400 perhaps degrees centigrade, and then it stops suddenly at a certain point here, when the temperature of the particle has reached more or less the bed temperature after 100 seconds. Then the path is very much simpler. The temperatures are the same on the surface and the center, and it goes on. In fact, the temperature is a little higher, few hundred degrees perhaps higher than the surrounding the reactor temperature, which was 800 degrees. And then it goes on like this until it stops, because it attains the reactor temperature and the combustion is finished at a little less than 500 seconds. This is what happened. And I used to ask the question, what has happened here? In this virtual situation, it is difficult to ask the question, so I have to answer it itself. The reason why there is a difference between the center temperature and the surface temperature is that the pyrometer sees, the pyrometer is directed on the surface of the particle, but it sees a flame from the particle. I said it was char particle, but it is the volatilizing particle, obviously. So volatiles are released until the particle is devolatilized, and then they are ignited and form a flame here with a high temperature. So what you see here, what the pyrometer sees is a flame, while the thermocouple measures the temperature inside the particle, and it is of course not affected by the flame. And then when the flame is finished, the volatilization is finished, then we have the char combustion. And then at the time of char combustion, the temperature is the same at the surface of the particle as in the center. Then it goes on until everything is burnt. That is the first case. In the fluidized bed, we cannot measure its external temperature, but we can measure the center temperature. And what we measure is the temperature which is a little higher than in the first case. It's a little higher, and you could speculate that this is maybe because the particle is heated a little faster in the fluidized bed than in the heat transfer is higher in the fluidized bed and here. But after all, the heating is controlled not so much by the heat transfer, but by the thermal conductivity. So the difference is not very big. And then the temperature keeps the same, so it's no difference. Okay, so we continue making the next experiment, and that is again at 800 degrees and 5. But now we don't have 21% oxygen, but only 5% oxygen. We repeat the same thing, measure the same things. In this case, we didn't measure here, I don't know why actually, but we measure in the open reactor. And what we measure then here in the beginning, not an increase in temperature, but a lower temperature. Then, the central temperature was increasing, but here we measure a rather low temperature. And only at this point, the two temperatures inside and outside are the same. Then it goes on till the end. And the end is at about 2000 seconds. And here it was only 500 less than 500 seconds. So you can see some differences between the two cases. In this case, the volatiles were emitted, but they never ignited because of the low oxygen concentration. They did not ignite, so there was no flame in this case. And the temperature was a little lower because the surface temperature was increasing, but it was still lower than the reactor temperature. And then when the volatilization was finished, we have the char combustion, but here the excess temperature was much smaller. It was not a few hundred degrees like in the first case, but it was only a few tens of degrees, not so much, and the time of combustion was long. So you see that the oxygen concentration also controls the time of combustion of char, and of course the ignition is important in such a situation. So I think this simple experiment reveals quite a lot of the conditions on a particle, but I should have written here fuel particles, and it was a wood pellet. Okay, so let's continue. I have previously defined the reaction rates, and like this, related to mass, and it could be related to the external surface I showed previously. So then again, I can transform it back to mass, but then if it is the surface reaction rate, the relation to mass reaction rate is this. And the units, you see, are a little different here. Okay. We have here the stoichiometry of the reaction. This is the moles of reaction. Certain number of moles of reaction react with a certain number of moles transported, but the transportation mechanisms doesn't know so much about the moles, so it has to be corrected here. It is translated into moles by the molar mass of carbon here, and the molar mass of the gas multiplied by the reaction, what is it called, the coefficient of reaction. 1 mole of carbon reacts with a certain number of moles of the gas that is included here. And these two together, it can be written in a more compact form, where we have then the stoichiometric factor, which is omega. And in this particular case, we have this stoichiometric factor. It comes into the reactions and the considerations in the following. So this is why I want to define it. If we have, for instance, this reaction, we have this type of stoichiometric factor. This is the molar mass of carbon, molar mass of oxygen, and the stoichiometry is 1. It is just 1 here. Here the stoichiometry is a half. So then we have to have half here. Otherwise, the molar masses are the same.